Next topic is Swirl Flow. Good charge motion within the cylinder will produce high turbulent level at the end of the compression stroke, because this high turbulence will increase the combustion speed and thus shorten the combustion duration. And as I mentioned to you in the previous slide, that the turbulence will decay quickly. So we need to design the intake system so that it will encapsulate most of the inlet jet into organized motion. So one of the organized motion is called a Shoal Flow. Swirl is defined as organized rotation of the charge about the cylinder axis. So it is created by bringing the intake flow into the cylinder with an initial angular momentum. So in this case, the intake system, especially in the intake port, is designed in such a way that the inlet jet will create a swirl flow, a rotating flow about the cylinder axis. While some decays in swirl due to the friction, we cannot avoid this one because we have a non-slip wall. So we have non-slip liner wall, non-slip piston wall, non-slip head wall. So uh, there will be a decay of this swirl during the engine cycle. So in this case, the intake generated swirl usually persists through compression. For sure there will be some decays, so at the end of the compression we'll have some decays of the swirl, and then we'll have some swirl during the combustion. So depending on how can we convert this swirl into the turbulent, we might still see some swirl during expansion process. In engine design with a ball-in piston combustion chamber, the rotation motion set up during the intake is substantially amplified during compression. So in this case, we have a ball-in piston that will create a squeeze zone. So we'll have a look in the next slide about the squeeze zone. So this squeeze zone will amplify the swirl flow, and some of this swirl flow will be converted into the turbulence when the piston approaches the top dead center. Swirl is used in diesel and some stratified charge engine concept. So in diesel engine, the swirl is used to promote more rapid mixing. So I should have one animation in chapter 10 when we look at the diesel combustion. So the swirl is used to enhance or to increase the interface area of the spray in contact with air. And the swirl is also used to speed up the combustion process in spark ignition engine. So we see this swirl utilization for combustion process in spark ignition engine when this engine was converted from a diesel engine. So right now we have several ongoing projects that convert a diesel engine into natural gas engine, and the parent diesel engine usually use a swirl type flow, and then we maintain this swirl type flow when the engine is converted into natural gas engine. This picture is showing an example of the swirl flow. It is viewed from the top, so you can see here clearly that the swirl flow is rotating counterclockwise, so it is in this direction, and the cylinder axis should be somewhere here. Okay, so this swirl flow happens during the intake stroke, and then it will get amplification during the compression stroke. Some of the swirl will decays into thermal energy due to the wall friction, and then at the end of the compression stroke, the swirl flow will be converted into turbulent kinetic energy. Some will still alive, and you can still see the swirl flow during the expansion process. In two-stroke engine, this swirl flow is usually used to improve scavenging. I think chapter 6 I show you an example of the scavenging strategy. So in this case we generate a kind of the swirl flow when the fresh mixture entering the chamber to enhance the scavenging process. In some design of pre-chamber engine, so we have a pre-chamber design for diesel engine and then some large engine with spark ignition type combustion. So this organized rotation is generated about the pre-chamber axis, and it's also characterized as a swirl flow. In pre-chamber engine, where swirl within the pre-chamber is important, the flow into the pre-chamber during the compression process create a rotating flow. So during the compression process, there will be a flow from the main chamber into the pre-chamber, and this inflow create a kind of rotating flow about the pre-chamber axis. Next one is looking at the swirl measurement. The nature of swirl flow in actual operating engine is difficult to determine. So in this case, we need to use an external device to measure this swirl flow. So a common technique for characterizing the swirl within the engine has been to use a light paddle wheel, and this paddle wheel is pivoted on the cylinder center line, and then usually it is mounted between 1 and 1.5 bore diameter down of the cylinder head. And then we have also another technique which is more precise. So this is using impulse swirl meter. So in this case we use a honeycomb flow straightener that replaces the paddle wheel, and then this honeycomb will measure the total torque exerted by the swirl flow, and this technique principally equals to the flux of the angular momentum through the plane coinciding with the flow straightener upstream phase. This picture is showing a schematic of a steady flow angular momentum flux swirl meter. On the top you can see the top view of the engine. So this is the intake side and this is the exhaust side, and then this one is the cutaway about the intake side. So you can see this is the intake system and this is where the fresh mixture entering the engine. So, and then this one is the honeycomb flow straightener that is used to measure the swirl flow. So we have such a type of swirl measurement at Southwest Research Institute, and we use it regularly to estimate the swirl flow of different engines. Next one is looking at the parameter to quantify the swirl level. When swirl measurements are made in an operating engine, a swirl ratio is normally used to define the swirl level. So this swirl ratio is defined as the angular velocity of a solid body rotating flow, omega s, that has equals angular momentum to the actual flow, divided by the crankshaft angular rotating speed. So equation 8.30. So this is the angular velocity, and this one is the crankshaft angular rotating speed. So 2 times pi times n. N is the engine rotating speed. Okay, so typically value for swirl ratio are in the range of 1 to 4. So typical range usually we have around 1.5, 1.6 for kind of large engine spark ignition. And if you want to have a higher swirl flow to enhance the mixing process, for example in the diesel engine, we can have the swirl flow up to 3 point something. How do we generate the swirl? There are two general approaches that is used to create swirl during the induction process. So in one, the flow is discharged into the cylinder tangentially, where it is deflected sideways and downward in a swirling motion. So in others, the swirl is largely generated within the inlet port, and the flow is forced to rotate about the valve axis before it's entered the cylinder. So the first one is by directing the flow tangentially, and then it's deflected sideways so that we have a kind of swirl flow. Second one is by generating the swirl flow before it's entering the cylinder. The former of motion is achieved by forcing the flow distribution around the circumference of the inlet valve to be non-uniform, so that the intake flow has substantially net angular momentum about the cylinder axis. And then the second broad approach is to generate swirl within the port about the valve axis prior to the flow entering the cylinder. So this is what we have seen most of the time. So we have a specific design of the port that will generate the swirl flow right before entering the cylinder. This picture is showing a different type of the swirl generating inlet port. So A here we have its kind of deflector wall, and then B here is a directed. So can imagine it will direct the flow entering the chamber and then deflect it sideways, and it will generate the swirl flow when the flow is moving downward. And this C is a shallow ram helical, so imagine you will have a kind of the swirl flow when it's enter the cylinder chamber. And this one is steep ram helical, same thing, so it will generate a swirl flow when the flow is entering the cylinder chamber. Swirl will be modified within the cylinder. One of this is because of the flow friction at the wall that will decrease the level of the swirl. So the next one, swirl can be also broken into turbulence during the intake and compression stroke. So we cannot encapsulate 100% of this organized flow. Some of this organized flow will be converted into turbulent. We can increase the swirl flow by having a suitable design of the combustion chamber. In this case, we use a kind of the squeeze zone. So we need to have a ball-in piston to generate a squeeze zone that will amplify this swirl flow. In diesel engine, swirl is used to obtain much more rapid mixing between the fuel and air. So in this case, the swirl is used to increase the interface between the fuel spray and air. The swirl can be increased by having a compact ball-in piston. So in this case, the squeeze zone is created when the piston approaches top dead center. So the phenomenon of the swirl increase can be analyzed by applying conservation of the angular momentum. So as the moment of inertia of the air is decreased, the air angular velocity must increase. The second organized flow that is used in engine is tumble. Tumble is charge motion about an axis orthogonal to the cylinder axis. So this is perpendicular to the cylinder axis. This tumble flow is usually used in spark ignition engine to speed up the combustion process. I think we talked about this combustion process in chapter 2, chapter 3, and we will look at in more detail in chapter 9. Having a faster combustion process is good from the thermal efficiency perspective. This is the way to set up the tumble flow in spark ignition engine. So usually we have a pan-roof combustion chamber with a 4 valve and then with inclined valve stem. By positioning the intake port to bring the entering airflow into the cylinder through the upper portion of the open area between the valve head and the valve seat. I have an animation for this tumble flow later. And then the descending piston then pulls that flow down the liner on the side opposite to the intake valves. It then moves back across the piston crown and upward along the liner to complete the rotation of the flow. This picture is showing the schematic how tumble is generated in a spark ignition engine. So this is the intake side. So this blue arrow is showing the flow direction that generate a tumble flow with the axis perpendicular to the cylinder axis. So key feature here is a low angle intake port. So it is about 15 degrees that direct the flow primarily through the upper portion. So this is the upper portion of the open valve gap across the cylinder head. So we have a minimum flow through this side, so that most of the flow will go through this upper portion that will generate a kind of tumble flow. In this slide, I will show you the simulation of the tumble flow by using a CFD, computational fluid dynamic tools. On the top left is the baseline intake system, and then we modified this baseline intake system. In this case, we have intake system A and intake system B. So the objective is to have a new intake system with a higher tumble flow and thus higher TKE and thus better combustion process. And the color here represent the level of the velocity, and then the line arrow show the direction of the velocity. And the simulation will start from the intake stroke, and then the piston will move down during the intake stroke, and then it hit the bottom center and then move up for doing the compression stroke. There is no combustion process in this simulation. You can see in here the intake system is on the left side. So now the intake valve open, you can see an inflow entering the chamber, and it's generate a tumble flow, and the tumble flow direction is clockwise. So you can see clearly here. And from the color, you can see there that intake system B has the highest of tumble velocity compared to the intake system of the baseline engine. And now the piston is moving up doing the compression stroke. Next one is the tumble flow measurement. The measurement principle is similar to the Shoal Flow measurement. So in this case, we use a honeycomb flow straightener to estimate the tumble flow for different engine. So this one is showing the top view of the engine. We have one intake valve and one exhaust valve. This is the cutway of this engine. I think it is about this line. So this is the cutway of the engine. So you can see in here is the inflow entering the engine, and it will generate a tumble flow, and this tumble flow will be measured by the honeycomb flow straightener device. How do we quantify tumble flows? The tumble flows are characterized by a tumble ratio. So this is analogous to the Shoal ratio. So the tumble ratio is defined as the ratio of the angular velocity generated by the tumble flow divided by the engine speed. So 2 times pi times n is the engine rotation speed. The tumble flow ratio, or the tumble ratio, is usually between 1 to 4, can go even 5, 6. If we generated a high tumble flow, we need to pay attention a bit on the bulk flow around the spark plug, because it might overstretch the spark and generate misfire. Next one is squish flow. Squeeze is the radial or transverse gas motion that occurs toward the end of compression stroke. So this happens when a portion of the piston face and cylinder head approach each other closely. In spark ignition engine, we can generate this squeeze by having a pan roof cylinder head. So the piston can be flat, and then we can have a pan roof cylinder head to generate this squeeze. Or we can have a flat cylinder head and a ball-in piston, which is typical in diesel engine. So with this ball-in piston and flat head, we can also generate a squeeze flow. The squeeze is also used to break the swirl into turbulence. So otherwise, we will still have a decent swirl during the combustion and the expansion stroke. This figure is showing a schematic of how the squeeze is generated inside the cylinder chamber. On A here, we use a kind of wedge-shaped combustion chamber to generate a squeeze. So this is the transverse motion, which is the squeeze. So as the piston moves toward TDC, we will have a squeeze zone here that will generate a transverse velocity. And on the right side, this is a kind of squeeze generation using a ball-in piston. So we have a flat head, but the piston here, you can see at the bottom here, the piston has a kind of the ball-in type piston. And this is the squeeze zone that will generate a transverse motion. Why do we need to have a squeeze? One is for sure we need to break the swirl into the turbulence. It is the turbulence that is used to enhance the combustion process, not the swirl. But you know that swirl is also still useful to enhance the fuel mixing process in diesel engine. But from the combustion perspective, we need a turbulence to enhance the combustion process. This is another feature to generate a squeeze flow. On the left side, on A here, we have a axis symmetric pull-in piston. So it is symmetry about the cylinder axis here. And then on B here, we have a wedge chamber with transverse squeeze. So the squeeze zone is on the right side here. Okay. While on A, you have equal squeeze zone on the left and on the right side of the cylinder axis line here. The squeeze velocity can be estimated by doing a simple analysis. This feature is showing the schematic of the squeeze velocity analysis. So we have a VSQ here as the squeeze velocity. So this is a transverse velocity from the squeeze zone into the central of the chamber. And then by applying a momentum conservation equation, we can get the squeeze velocity as a function of the bore and then ball-in piston diameter, and then C here is the clearance height. The feature on the left side is showing an example of the squeeze velocity normalized by the mean piston speed as a function of engine crank angle. We have several lines here that represent different ratio of dB over B. So once again, dB is the ball-in piston diameter. So as you can see here, as we increase a dB, which is the ball-in piston diameter, we have a lower squeeze velocity. So this makes sense because we will have a smaller squeeze zone, and smaller squeeze zones means we will have a lower squeeze velocity. Next topic is Prechamber flow. So we have several ongoing projects on this Prechamber design. So there are two types of Prechamber. So one is called active Prechamber. So in this case, we have additional fuel injected into this Prechamber. Second one is what is called passive Prechamber. So in this passive Prechamber, we don't have additional fuel injected to the Prechamber. So all fuel is injected to the main chamber, or it is injected in the port of the intake system. Historically, small high-speed diesel engine use this prechamber to enhance the combustion process. So in this case, the prechamber is connected to the main combustion chamber above the piston via a nozzle. So this one is showing the schematic of the main and prechamber. So this is the prechamber. So this one is the prechamber, and this one is where we have the nozzle. So this one, we have the nozzle that connects the main chamber to the prechamber, and then flow of air through this restriction into the prechamber during the compression stroke set up a high velocity in the prechamber at the time the fuel injection process commences. So in this case, we talk about the active prechamber. So because of this nozzle type passage, we have a high velocity entering the prechamber that will enhance the fuel air mixing process inside it. Next topic is crevice flows and blowby. Crevice, it is a small volume that is connected to the combustion chamber. So it's called crevice because of its narrow entrance. We have several crevices in internal combustion engine. So we have a crevice around the spark plug, and the largest crevice is the volume between the piston rings, and cylinder wall. Okay, and some gas flow in and out of this region because of the pressure difference between the crevice pressure and the cylinder pressure. So at one instant there will be a flow into the crevice, as for example during the intake stroke, and at other instant there will be a flow out of the crevice into the combustion chamber, for example during the later part of the expansion stroke. And this is one of the source for the unburned hydrocarbon, because the fuel got trapped inside the crevice, it didn't burn, and then it will flow out of this crevice and exit the engine during the exhaust stroke. Some gas flow out of this crevice region through the ring packs, okay, ring packs and ring caps, and into the crankcase, and this flow is called a blowby. So this is a flow losses. This is a losses of air and fuel because it flows from the combustion chamber into the crankcase. Other crevice volume in production engines are the thread around the spark plug, okay, and then the space between the plug center, electrode, insulator, and casing, and then the crevice between intake and exhaust valve head and seat. And this table is showing an example of the crevice volume compared to the engine displacement and then a clearance volume. So this is for the engine with compression ratio of 11.2. So we have 100% of the displaced volume per cylinder, and the piston crevice is about 1.7%, and then we have spark plug crevice 0.4%, and this one is for valve seat and head gasket crevice, so it's about 0.08%. So the total crevice volume is about 2.3% of the total engine volume displacement. And this feature is showing schematic of piston and ring assemble in automotive spark ignition engine. So in this case we have a 3 ring. So we have a top rings, and then this one is the second ring, and this one should be the oil rings. So this is the combustion chamber. When the blowby occurs, we will have a gas flow from this top going down. So some will flow through this path, the other might go directly through this path, and same thing here. Okay, we have this path, the other this path, and finally some of the flow will go into the crankcase here. So this is called a blowby flow. Okay, we have completed this chapter 8 discussion. Stay safe, especially during this COVID-19 pandemic period.